Welcome back to another video. This video I'm recording after more than a week because I'm here in Pakistan and been busy with different thing here. Anyway, let's get started. Today's topic is subtraction and comparator. So this and this one. Uh, we are on combinational circuits, and I'm making different higher level components, circuits that can perform very useful operations on input data. And they did adder, couple of type of adder, and let's look into subtraction and comparators. So first, subtraction, you will see that the adder that we studied is a very important component, because that's not only used by just addition, but it also part of subtraction and also part of multiplication. So look into that. So let's say we have a number a and b. So we want to do a minus b. In other words, a plus minus b. So minus b, like a negative number. So making negative of a positive number b means we need to find out 2's complement of b. And how do we calculate 2's complement of something? Well, first we invert every bit, we flip the binary number, and we add 1. So all we have to do is calculate this one when we want to subtract b from a. So a plus b invert plus 1. Let's look at this example. I already created an example for you. So this is a 1, 2, 3, 4, 4-bit number. The most significant bit is sign bit. This is 6 and this is 2, and both are positive. Then you want to calculate 2's complement of 2, because this is our a and this is our b. So let's follow this one. So we want to find out this thing. So first component is b dash and then b dash plus 1. So b dash, literally this is b, this is 2. All you do is flip every bit. 0 becomes 1, 1 becomes 0, 0 to 1, 0, 1. Then we do b dash plus 1. So we add 1 to this number. So let's add 1, 1, 0. There is a carry 1. So then 1, then 1, then 1, and then 1 here. Okay, so this is a number which is by flipping then adding 1. So this is the negative minus 2. So all we have to do is now the number a is 6, equivalent of 6 in binary, and then we have to add this b dash plus 1, which was this number. So let's add these two numbers. 0, 0, 0, 1, 1 is 1, 0, so 0 is here, 1 is carry. 1, 1, 1 is 11, 1, sorry, I shouldn't say 11, 1, 1. So 1 is here, 1 is carry, 1, 1, 0, and 1. Okay, this is a carry out. We are interested in these 4-bit number, which was what we had originally. So what we do is this number is, this is positive and this is 4. So answer is 4. So yes, 6 minus 2 should be 4. So this is how we calculate, just to give you a concept, an idea. But then you need to think of how are you going to implement this in digital hardware. Okay, our best friend adder, as I previously said, comes to our help. So what we do is, again, the same example here, 4-bit. So we have two numbers, a is 0, 1, 2, 3. So, and then b0, b1, b2, b3. This one I created before, sorry, I'm interrupting this discussion. I created just a concept wise there, but I'm using this one as related to this particular example. This is a generic symbol with n bits. So let's look into this and then when we generalize it. So you have 4-bit adder because there are 4 bits in each number. And for each adder you have A, and A1, B1, A2, B2, A3, B3. Now how you probably be thinking, how are we going to, this is just an addition, or you put A. So yes, so first we need to do is we need to calculate B. Okay, so let's do that. We need to create inversion of every bit, not A bit, B bit. Inversion is inverter. Then we're done with this step. So then we have to add plus 1, mean just 1. We're not adding 1 to every one of them, okay? Just a one single one. And the single one, the easy way is this Cn that is coming into the adders, we just fix that, hardwire that to 1. Okay. Or in other words, if we have a generic adder, what we can do somewhere is put a multiplexer there. We studied multiplexer. Now we are using those circuits. 1 and a Cn. So what happens is we need to select. So when we want to use this adder as a subtractor, okay, then we need to make sure we have B inverted, and then we have 1 comes here. Through select, we need to make sure select is selected such that this comes here. And then first one comes, so in a way we are adding A plus B dash plus 1. So the answer is Y0, Y1, Y2, Y3 will be the right answer. And the carry out from here, that is something we are ignoring, discarding, because we have a 4-bit numbers. Probably be thinking why I didn't add, if you want to use this, oops, my bad. If you want to use this adder as a adder and subtractor, then one other thing you can do is you can add a multiplexer there. Sorry, here. And you can have on one side you have B inverted, oops, B inverted, and the other one is B, and then the output of multiplexer will go here. So if through multiplexer you select B, and by the way the same multiplexer will be everywhere. I'm just putting this thing here, doesn't have much space. This is multiplexer, and all these multiplexers will have a select line. Maybe we select such a, not say multiplexer. So now you are seeing also how those simple circuit multiplexer and adder we are using those for completely different purpose here. And that's what this digital design is about. Once you create your basic elements, you can start combining elements to change the functionality of it. And the same thing, once you select proper multiplexer, instead of an adder, it becomes a subtractor, A minus B. Okay, this one now we can, if we can make a 32-bit subtractor by using 32 adders like this. So you can say that for a subtractor generic symbol, so Cn will always be 1, then B you need to invert. Doesn't matter how many bits you have, you need to invert all those bits and bring on to the adder, and then the other side you have A, same n bits, and you keep the output bits, and the carry out is from here, which you discard. That was subtraction. Hope you understood that. Let's cover comparators and other combination circuits. Why we need comparators? Because we want to compare two values. So if A and B, we want to compare whether A is equal to B or not, so equality comparator. Then A is greater than B or A less than B, these are magnitude comparator. And these are the operations that you probably be thinking why you keep adding more, but you will see later on when I'm gradually going into microprocessor design, because microprocessor is a core component of computing, and a very flexible and very powerful, as you can program it and the same hardware can do a lot of different things. Anyway, we will touch into computer architecture when I get there, but right now think of these, all these are basic key components that you can put in an arithmetic logic unit of a microprocessor, and then that unit is fixed and now you can use it for different basic operation, and using basic operations then you can do a lot of complex operations. So these are the three key things in comparator. Let's look into equality first, and I'm starting with a very simple example. We have only A is just 1 bit, B is 1 bit. That's the simplest example, correct? You can have a 0 0 0 1 1 0 1 1. When 0 0, that means it's equal. When it's 1 1, it's also equal. When they're 0 1 1 0, they're not equal. Simple, isn't it? Now all we need is have a block where, sorry, this place is too congested. A comes, B comes, and have a signal here, which is when is 1 means A is equal to B. If it's 0, then we will think that A is not equal to B. So we are now, this is a very good example. Now we are trying to using a truth table, trying to create that circuit. So in another way, when you say, hey, A is equal to B or not will be, how digitally you can transmit that information, how you can tell somebody digitally, and you will tell digitally by using gates. And so here we are using what kind of gates we use and how do we use them to output this thing. So this is our goal, and we're trying to figure out this thing in the middle. So if you think this thing, like think of an exclusive OR. Whenever 2 bits are 0 1 1 0, okay, exclusive OR, then when it's odd bits, it becomes 1. But what we want to send is when they're equal, there's 1, but in this case it's 0 and 0. But we actually want to send 1 when it's equal. Well, you can design in different ways, but this is one way. So if you do an exclusive NOR, or all you have to do is put a NOR and what at the end, and it will this. I think this perfectly explains what we want to produce. So look into this. All we have to do is A0, B0, A1, B1, we are 4 bits, okay? This is single bit. So if you think just 1 bit, it's an exclusive NOR of A and B. But if you have a lot of bits, you want to make sure that each one is 1. And you want to put an AND gate. Quality of AND gate is if all of them has to be 1 in order output to be 1. So in this case, this is an equality. Whenever A and B 4 bits are exactly equal, this signal will be 1. Otherwise, it will be 0. You probably be thinking, okay, is there a way we can do all this using an adder? Because if you subtract A minus B, you already have an adder which you're using for different purposes. What if we use it for this purpose? Well, answer is yes, we can. So if we, let's use this circuit. We don't need to redraw this. So if a minus b we do, and answer is 0, that means a is equal to b, correct? So if a, let's use that one then, a minus the subtractor that we use. Here we go, we have immediate example of application of that subtractor we create. If all these, oops, this is not a pointer. If all these become 0, then that means it's 1. Oh, but how do we do that? How you detect? So if I ask you, create a circuit that becomes 1 when y3 to 0 is equal to 0. So first of all, you need to say that, okay, we need to have okay, or will ensure that when all these become 0, this will become 0, and then you put an inverter, which means it's a NOR. This will become 1. So let's say whenever these become 0, this becomes 0 and this becomes 1. Let's say if one of them is not 0 and 0 1 0 0, so that means this will be 1 and not will be 0. So using just putting this NOR gate at the output of this, we can totally turn this into an equality comparator. And these are the important flags that you are finding now. It's an equality flag. So all we do is whenever this signal is 1, I mean these numbers are equal. So now you can generate different circuits at the output. So for where we need simply use this one, we don't need this output. We will simply use from them. By the way, you don't need to create a, for example, if you are doing something like this, let's say this is 4-bit adder, this has 4 bits. One way is you can use here like a NOR, but you can also take them for something else, and they can be used somewhere else. Maybe that data you can write into the memory or into the register, which we're going to study under sequential. So now we are gradually adding more complexity. Okay, let's look into comparison of A and B, and saying, okay, whether A is greater than B or not. Okay, and let's define something similar in this case. So when A, okay, yep, and A is in B, we maybe do this, sorry, oops, I should have left some space here for my dribbling. What we want to do here is A, B, and again is A bigger than B. This signal needs to be 1 when A is greater than B, and if it becomes 0, that will should indicate A is less than B. So question is how we figure this out. Okay, think if using adder we can do something like this. You'll probably be looking at it already, but if you think how we can use same thing, a subtractor, for that purpose. So what if we have A and two numbers that we're comparing, we do A minus B, and the resulting number B, using the same circuit so I don't have to redraw it. Now if this bit is 1, means the output is negative. Now it doesn't matter what values these have. If this one is a negative, that means B was bigger, right? That means if this sign bit, the sign bit, let's say this is sign bit. If we take this out, that's just sign bit. This bit is we have taken out. But it will be when 1, that means A is less than B. Alright, so then we can flip it, put an inverter there. And now in this case, whenever A is greater than B, this will be 0. And with 0 comes here, output will become 1. So we achieve this. When A is less than B, B will become 1. Sorry, this most significant bit, which is the sign bit, this will become 1. And then we have an inverter, the output becomes 0. So we achieve this. So we have achieved this by again using an adder. So you see how this adder circuit that we created, that's why I spent a few videos on it, and look at ripple carry adder and the carry propagate adder, because those adders are super important in building other circuits. Hopefully you have understood it, and next time we will look into another important concept in this addition and subtraction. See you next time. Take care.